Hi, welcome to the channel. In this video, we are going to discuss different approaches for tokenization. There are primarily three different approaches: character level, subword level, and the word level tokenization. Subword level is the most famous one, which OpenAI uses for state-of-the-art models like GPTs. Let's discuss what are the different trade-offs associated with each of them, how selection of a particular approach impacts the overall system. Now, let's discuss about the trade-offs associated with each of the approach. We saw there are primarily three approaches for tokenization: character level, subword level, and the word level. So we are going to see how each of that approach fares on different criterias, and we are going to discuss how that impacts our overall system. Okay. So let's take an example sentence. Unbelievable players were replaying the match. If we look at the end result of the character level tokenization, then it will look something like this. It will break each of the individual character into one token. So there are going to be 39 tokens into it. And if we look at the other extreme word level, then it is going to assign one token or one token ID to each of the word. So there are going to be 6 tokens. Okay. So this particular approach, character level, is too fine. I mean, it breaks each character into one token, while here we get one token ID for each of the word. But a good balance of both of these approaches is subword level, where we break each of the word into reusable components. For example, if you look at the word replaying, then it is breaking this into a main word and then the suffix. So if we encounter another word in the sentence or data like replayed, then it will again break that particular part into replay, that is the reusable component of this word, and then the suffix like ed. So these are the common suffixes which we encounter in the data set: ing, ed, or like this s. Okay. So now let's talk about the different criterias. At first, token meaning. That means how much information each of the individual token is carrying. In character level, it is very low because, as we know, a single character doesn't convey as much information. Okay. Now, if we compare that to word level, then the information or semantic richness is very high here, because for each token we have the individual word. Subword level again balances it. The meaning or semantic richness is medium to high. It captures meaningful pieces. Okay. Now, talking about sequence length, because we are breaking the sentence into each of the character, we are going to end up with a very long sequence. For example, here we have 39 tokens. The other end, it is going to be very short because each word will be associated with a token. So we have only 6 tokens here. But because subword level breaks into reusable component, we are going to have some tokens in middle of these two extremes. So it is moderate. Token frequency, it is very high because characters repeat a lot. On the word level, many tokens are rare. In the entire data set, many of the words are there which are not that much frequent. Now, what impact it is going to have on the model training is the words which are rare or which doesn't occur too frequently, they are not going to get trained as efficient as the words or tokens which are much more frequent. Because of that, we are going to have embeddings corresponding to that token not trained very significantly, that in turn contains glitch token. We are going to discuss about it more, how glitch tokens can create issues in the entire system. But right now the point to remember is it is not good to have many tokens which are rare, long tail. Sorry for the typo here. Okay. And then we have a balance in the subword level, so it's high. The token frequency is high because of the reusable component, so it creates a good balance. Now, talking about the learning efficiency, because each of the character or token contains very less information, so the learning efficiency is going to be low. The attention mechanism which we know in the LLMs is going will find it hard to learn from the individual characters. Again, here low for rare tokens. So the learning efficiency, as I mentioned earlier, it is going to be low for rare tokens. Sparse learning, that means the embedding for those tokens won't be learned appropriately. Now, from a system design point of view, if a particular input contains glitch token after training, assuming that we have trained the model and the time of inference in production system, if input data contains a glitch token, a rare token, then because the embeddings were not trained effectively for them, it can create hallucinations in the model. You might remember an example of solid gold magic carp related issue in the earlier versions of GPT models. And talking about learning efficiency in subword level, it is high because we have reusable components. Generalization to unseen words, it is excellent because any word can be formed from characters. So talking about this particular character level break, if we talk about the vocabulary, entire vocabulary, then we know that in the Unicode system there are around 150k different Unicode code points. So any word can be broken down into character level and can be represented here. On the other extreme, because each word contains its own token, so if we encounter at the time of inference a word which is not there in the training set or not part of our vocabulary, then there are very high chances that we will get out of vocabulary issues in this. Now, in the subword level, the generalization is excellent because it works specifically talking about the byte level BPE. It represents each of the word into byte sequences. Now, any word in any language can be represented in terms of bytes. That's why the generalization is excellent here. Now, morphology handling, as we discussed earlier about those suffixes, right? ing or ed. So it's possible, but at very low level in character level part, it is good in subword level. And here also it is poor. Now talking about embedding or output layer size, as we have seen earlier, tokenization is in turn going to indicate towards the first layer of the LLM system, that is the embedding layer. So the vocabulary size is directly impacting our input layer, embedding layer. In many of the earlier systems, both the input layer and the output layer was tied. So we have tied weights. In those particular cases, both the input embedding layer and output layer size depends on the vocabulary size, because the vocabulary size here can be small. So that's why we have a small, comparatively small embedding or output layer. On the other extreme, if you want to create a vocabulary on word level, then it is going to be very large, because in order to represent every possible word in the world across different languages, it will explode the vocabulary size and in turn will create a very large embedding and output layer size. In terms of system design, that directly impacts our model performance. It increases latency, it increases cost of inference, and it also can create out of memory issues in GPUs. So subword level provides a moderate embedding and output layer size, which we already decide at the time of tokenization training. Now, coming to the compute and memory, as we discussed, very small sequences or these particular vocab sizes, here the memory requirement or compute is going to be high because long sequences increases attention cost. Here we have the output layer which is expensive, but it is low per token, while the subword level provides a balanced view between the character and again the word level. Talking about multilingual scalability, so if we are serving a global user base, then we need our model to be trained on multiple different languages. So multiple languages can be represented on a character level, as we discussed earlier, with the help of Unicode code points of around 150k. But it is going to be very hard on the word level because, as we discussed, vocabulary explodes across different languages. Here, because we are representing word as bytes, so any particular character can be represented in terms of byte representations. Now, talking about overall strengths of character level, it gives us the maximum coverage in terms that every character in any other language can be represented easily here. It is simple, just break this individual character in the input text and we are done. Frequent tokens, because the tokens are frequent, learning in terms of frequency can be good, but in terms of semantic richness, the quality of embeddings might be low. Okay. Like as it is discussed here, the weakness about the character level, it contains too many tokens, weak semantics, and because it creates a larger sequence length, the compute will be high. Talking about the strength and weakness of word level, high semantic richness per token. Yeah. So as we can see here, each token represents a very good meaning. One token can entirely represent an word. It also creates short sequences, but the drawback is it has a huge vocabulary, sparse learning for rare tokens as we discussed, and poor generalization to new words because it can result into out of vocabulary words. Okay. Now coming to the subword level, it provides an overall good balance of meaning, frequency, efficiency, and generalization. The only weakness or drawback is it is more complex to train this type of tokenization. And we are going to dive into this particular method, byte level, byte pair encoding, in the upcoming part of the video. So summarizing this entire trade-off here, character versus subword versus word level tokenization. Character level is too atomic, frequent but not meaningful. Word level is too specific. Each word or each token has a good meaningful representation, but it might result in huge vocabulary and out of word issue. So the subword level is just right, a good balance between character level and the word level. It breaks input text into reusable components and which are also meaningful. So the winner here is the subword tokenization. It usually results in the best trade-off between frequency, meaning, efficiency, and generalization. That's all for this video. If you like the video, if you gain some insight out of this video, please like, share, and subscribe. Thank you.